or good afternoon, good evening, wherever you are. It's a great pleasure for me to participate in this virtual series, and very appreciative to Francisco and Andreas for setting it up. My topic is called Ghost Problems from Pauli-Villars to Fourth Order Quantum Gravity and their Resolution. A lot of the stuff I'm going to talk about I'd done quite a while ago, but there'll be some more recent stuff. I just submitted it to the Gravity Research Foundation, and it was given what's called an honorable mention. And I only mention that because I believe that it's, as you'll see, this is going to be a talk about PT. I believe that this is the first time that anything about PT has appeared in the essays on gravitation. Okay, so the Pauli-Villars regulator and the 70-year ghost problem. This problem has been around for 70 years. If you look at a typical Feynman diagram, a typical loop diagram, it's going to be divergent. And Pauli and Villars introduced a regulator for these divergences. Their primary objective was to implement gauge invariance. And what they basically did was they replaced this propagator, the standard single propagator, by a pair of propagators. And because of the relative minus sign, instead of behaving asymptotically as 1 over k squared, this object behaves as 1 over k to the 4. And so this quadratically divergent graph becomes instead log divergent. Now, if you read their original 1949 paper, they said it is a mathematical procedure, but they did not want to rule out the possibility that it might be physical. And we'll see that in fact it can be physical. And that's basically the point of the talk. Now, if you have this theory, you would have two actions, one to produce the first propagator and the other one to produce the second propagator. But how to generate the minus sign was you'd have to introduce a very unusual completeness relation where you have positive norms and then negative norms. But if you insert this completeness relation into this 2-point function, you would then obtain this propagator. So the difficulty that the theory has is that the price you pay for getting the improved convergence is an apparent minus sign, states of negative norm, loss of probability, and loss of unitarity. So that's the shortcoming, and we're going to see that this replicates in many, many different places. Peiss and Uhlenbeck in 1950 said, well, let's consider, rather than doing this two-field action, the one I gave you a moment ago, let's consider the possibility that we could produce the same propagator by a one-field action, but it was going to have to be a fourth-order theory. They wrote down this theory, there's the equation of motion, and they obtained the propagator 1 over k squared minus m1 squared, 1 over k squared minus m2 squared, and if you write it in partial fraction form, it generates the Pauli-Villars propagator with the relative minus sign. They then studied this theory, and rather than work with the full quantum theory, since time derivatives are the only things that are relevant to quantization, they said omega 1 is k squared plus m1 squared, omega 2 k squared plus m2 squared. And this action then reduces to what's called the Peiss-Uhlenbeck action. And the Peiss-Uhlenbeck action, you can see that gives you the z double dot, this term gives you the z dot squared, and this one gives you the z squared. So this is the quantum mechanics of the Pauli-Villars propagator. Now, it's a constrained system because you have a z dot, and a z double dot. So there are too many canonical variables for one oscillator, but not enough for two. So how do you make it into a two oscillator system, and how do you remove the constraint? You introduce a new variable, x is z dot, and you can construct a Hamiltonian. It turns out that Ostogradsky in 1850 had already worked out the rules for Hamiltonian, for theories where you have higher derivatives than just z dot. You can use his method, Aaron Davidson and I use the method of Dirac constraints, and the other way is to covariantize the action and vary with respect to the metric. And when you do this, you obtain the following two oscillator Hamiltonian, two sets of canonical variables, z and pz, x and px. Now, this is a regular quantum mechanics. There are no ghosts, but you pay a different price. This term here, the minus a half omega squared z squared, is negative, and that means the energy spectrum is unbounded from below. And this is known as the Ostrogradski instability that is characteristic of higher derivative theories. So they managed to find a field theory that successfully generates the propagator that they wanted. And now they'd avoided the ghosts, but they paid a different price. The theory has a spectrum that's unbounded from below and is simply unstable. Very interesting, at about the same time, Lee wrote a paper in 1954 called the Lee model, which I'll come back to in a moment. Kjellén and Pauli wrote a paper in the Danish scientific journal in 1955, and Heisenberg looked into this in a paper in 1957. Heisenberg was very interested in what's called the Heisenberg nonlinear spinor theory, which is basically the first attempt to write down a field theory of strong interactions. And all of these cases had a ghost problem. And it turned out that you could trade the energy instability if you did, in fact, quantize the theory with ghosts, namely you quantize the theory with negative norm states. So how do you see that? You just make the substitution. Z is, you do two creation and two annihilation operators, Z, PZ, X, and PX. You make that substitution. And Aaron Davidson and I showed that when you do that, this original Hamiltonian, the one upstairs, becomes this expression here, A dagger A, A1 minus A dagger 2, A2, plus a 0 point energy. And the crucial feature is that while the A1 dagger commutator is positive, the A2 dagger commutator is negative. When Aaron and I discovered this, we realized that this was actually going to be good news, as I'll come back to in a few moments. Now, as we'll also see below, if we are to set omega 1 equals omega 2, these commutators become singular. And we'll see that that's quite a significant feature. So we've got a regular quantum mechanics. We have a Hamiltonian, fully familiar Hamiltonian, A with A dagger, A2 with A2 dagger, and it has two separate realizations. The two realizations, the normal one is you just define the vacuum that A1 annihilates and A2 annihilates. And then what you see is, though there's a minus sign in the Hamiltonian, because of the second minus sign in the commutator, the A2 sector's energies are positive. So in fact, you finish up with an energy spectrum that's bounded from below. Omega is the ground state. It has the 0 point energy, a half omega 1, omega 2. But if you look at the excited state A2 dagger omega, which lies at omega 2 above the ground state, it has a Dirac norm vacuum A2 dagger vacuum that is, because of this minus sign, is negative. So you can avoid states of negative energy, but in turn, you have to have states of negative norm. Now, there's another realization of this, which is to set A1 and A2 dagger annihilates the vacuum. And the theory instead, because you've flipped the role of the A2 and the A2 dagger, this now becomes a positive commutator. So now there are no negative norm states, but this term here with the minus sign gives you an energy spectrum that's bounded from below. And why is it negative energies? Because A2 dagger would propagate negative energy states forward in time. So these are the two realizations. Realization one is energy spectrum bounded from below, Dirac norm negative. The other one, energy spectrum unbounded from below, but no negative norm states. So either way, it looks like bad news. However, I just want to stress that nonetheless, all the energies are real. And we'll see that this is of significance in what comes next.
Can I interrupt at this stage, or is it allowed?
Absolutely, yes. It's the only way I know that anyone's there.
How bad news is that you found unbounded from below spectra? Could it not be possible that quantum corrections will bind them, like what happens, for instance, or this is a pure non-perturbative? I mean, do we know that the spectrum is truly unbounded from below, or quantum corrections could save that?
Okay. There has been no demonstration that quantum corrections would modify this. However, there was a paper by Smilger who added on an additional interaction, which then gave you a lower bound on the energy. So it has been looked at.
Okay, thank you.
Okay, but I don't know, Andre, is Andre there this week? And maybe he could comment. But otherwise, I would say in summary, the Pace-Uhlenbeck theory suffers from one of two twin diseases, either negative norms or negative energies. However, you can define the vacuum as A2 on the vacuum is zero, or A2 dagger on the vacuum is zero. They are different Hilbert spaces. So they correspond to different Hilbert space realizations of the theory. In no single Hilbert space does one have both diseases, though in either one there is a problem and it is seemingly irrefutable. So that's been the wisdom of this model for many, many years. The next thing happened, Lee and Wick in 1970 looked at the same Pauli-Villars propagator, but continued it in the mass into the complex plane and took two masses, m squared minus I gamma and m squared plus I gamma. And then even though there's a relative minus sign, when you add them together, you produce minus 2I gamma over k squared minus m squared squared plus gamma squared. And if you just compare that with the standard bright Wigner, 1 over k squared minus m squared plus I gamma only, just the first term, its imaginary part is negative, just like the imaginary part of the Lee-Wick propagator, and therefore this is now a unitary theory. And so they argued that they can make the Pauli-Villars propagator unitary. They solved the ghost problem, but only with unstable rather than stable states. Quantum gravity. The next place where this issue appears is standard Einstein gravity is based on the Einstein-Hilbert action, and it's the Ricci scalar is a second derivative of the metric, and therefore the propagator is of the form 1 over k squared, and that's the reason why Einstein gravity is not renormalizable. How could you make a theory of gravity renormalizable? Well, try to get a 1 over k to the 4 propagator. Sounds rather familiar. It's like Pauli-Villars goes from 1 over k squared to 1 over k to the 4. Try to reduce the divergence at infinity. For that, you will need, instead of the Ricci scalar, you'll need the square of it, because then you have 4 derivatives. And the cleanest version is the so-called Weil action, in which you demand an invariance under local conformal transformations, and that leads you to an action which is Ricci tensor squared minus a third Ricci scalar squared. And I have been working on this now, I can see from 1989 to 2020 is 31 years, and you'll see that it's led me in. I would never have expected when I started working on this that this would have anything to do with PT symmetry, and we'll see in a moment it does. And so we get a 1 over k to the 4 propagator, and now the theory is renormalizable. A halfway house would be to have both, to have second order and fourth order. And then you can find a gauge in which you precisely have an action with acceleration squared, velocity squared, and coordinate squared. Namely, this action that we've already been looking at would be the action of second order plus fourth order gravity combined, and would lead to the same Pauli-Villars propagator with the 1 over k squared minus m1 squared minus 1 over k squared minus m2 squared. Now, these theories are very much in vogue at the moment. There was a whole conference at Cern just a year ago on the topic, as they provide a renormalizable, because of the 1 over k to the 4, renormalizable theory of quantum gravity. So, no string theory, no extra dimensions, no supersymmetry. All of these have not been confirmed at the LHC, which was built, that was one of its objectives. But nonetheless, there is a renormalizable theory. However, what about the ghosts? So we're almost there, but we're still at an impasse. So we see that the Pauli-Villars propagator is appearing in many different places, but nonetheless, the ghost problem has not gone away. And now I'm going to show you how it goes away. PT symmetry to the rescue, the Lie model. When Lie introduced this model, the interest in it was that you could do coupling constant renormalization analytically, rather than just do it perturbatively. The model, unfortunately, did have ghost states of negative norm, and as I mentioned, Lie, Chilenan, Pauli, and Heisenberg worked very hard on the issue. The problem remained unsolved until the work of Carl Bender and Brandt and Chen and Qinghai Wang in 2005, namely no less than 50 years later. And what did they found? They found that the ghost states only appear for a certain range of the renormalized coupling constants of the model. But since you can do coupling constant renormalization analytically, they tracked back and they found that in that range where there was the ghost, the Baer coupling constant is complex. And in that case, the theory is not a Hermitian theory. And if it's not a Hermitian theory, you cannot use as the inner product the overlap of a Ket state with its Hermitian conjugate bra. You can only do that in a Hermitian theory. However, they found that the theory had an antilinear PT symmetry. And when one uses the PT theory norm, namely the overlap of a Ket with its PT conjugate, one finds that the norm is positive definite. So the seeds of the saving of the theory was that the ghost states appeared in a regime or domain where the coupling constant was complex and the theory wasn't Hermitian. Solving the Lie model ghost problem this way is, in my opinion, a considerable triumph for PT theory. So what's the wisdom we can learn from this? In general, if one finds states of negative Dirac norm, it does not necessarily mean that the theory is not unitary. It could mean that one is in the wrong Hilbert space and that one is using the wrong inner product, the Dirac one, with a different inner product, the PT one, being unitary. So a theory that looked like it couldn't be rescued is rescued by this PT mechanism.
Philip.
Hello.
The solution of the problem is due to Bender, but the fact that it was non-Hermitian was already back to the times of Heisenberg and Lie.
Yes, but thank you. But I don't think they knew what to do. But nonetheless, it's not just recognizing that the theory was not Hermitian, but recognizing that you had to use a different inner product. And anyway, maybe Carl can fill us in some of the more background on that. But nonetheless, I think it's, however it is, the Lie model now is a viable theory because there is a way to construct a Hilbert space in which the norm is positive definite. Okay. Now, what about the Pauli-Villars and the Pauli-Uhlenbeck oscillator? Can we resolve those the same way? Now, if we write down the Hamiltonian, which I gave you before, unfortunately now there's no complex coupling constant. So staring at the Hamiltonian doesn't appear that it's not a Hermitian theory. Can we check if it's a Hermitian theory? Well, yes. You set Pz is minus id by dz, Px is minus id by dx, and the Schrödinger problem for this Hamiltonian becomes a very straightforward second order differential equation. You look at the ground state, the one with that 0-point energy, omega 1 plus omega 2 over 2, and you find, and Carl and I found this in 2008, that the wave function, which is solvable exactly, goes like e to the plus z squared and e to the minus x squared. So it's renormalizable in x, but it's not renormalizable in z. So the state diverges as z goes to infinity and is not renormalizable. Oh, 1 second. And it's not renormalizable. So now let's calculate the norm of the ground state. Just put in xz intermediate states and it just becomes psi star psi, and it's infinite. So the ground state is not normalizable. And therefore the excited states aren't either. And therefore your assumption that you could use the completeness relation with the relative minus sign doesn't hold, because it presupposes that the states were normalizable. So what we discover is there's a lack of normalizability. And the surprising thing is, it is the lack of normalizability that actually saves the theory. Namely, we have this wave function, I just gave it you a moment ago. It diverges. How could we make it converge? Continue z into the complex plane. If you consider the letter x in the complex z plane, the wave function is normalizable in a wedge that contains the north and the south quadrants of the letter x. This is a so-called Stokes wedge, namely the one that contains the imaginary z-axis, but not the real z-axis, because the real z-axis would be in the east and the west quadrants. So if we can continue z into the complex plane, but leave x where it is, we can make this wave function normalizable. The way that we did it was we made a similarity transformation, which preserves the commutation relations and gave us a new Hamiltonian with, and you notice that this one has a minus IQX term in it. Now, the energies are still real because we made a similarity transformation. So energy eigenvalues can't change. However, now the Hamiltonian is manifestly not Hermitian, yet its energy eigenvalues are real. Therefore, it falls into the PT category. It has a PT symmetry, X and Y PT odd, P and Q PT even, and has all energies real, which is the hallmark of PT symmetry. So when we make this transformation, we finally now do discover the complex coupling constant that we would like to see, and now we know that it's there. Now, this is still not a diagonal action, but we can diagonalize it. We introduce, and this is the standard procedure in PT studies, you introduce an operator Q, which is PQ plus XY, and you find that it transforms H into P squared plus Q squared plus X squared plus Y squared, which is about as benign and acceptable positive norm two-dimensional oscillator system as you can discover. Now, the phase here, e to the minus Q over 2, it's not e to the minus IQ over 2. So it's not a unitary transformation. Q is Hermitian. It's not a unitary transformation. It's a transformation from a skew basis with eigenvectors n to an orthogonal basis with eigenvectors n prime, and the kets are n prime this way. Now, because this is a two-dimensional oscillator, n prime is delta mn, and therefore working back, n e to the minus qm is also delta Mn. And therefore, we found a scalar an inner product, which is positive definite. If you check back and ask what are the eigenstates, we find that the right eigenstate of the Hamiltonian is n, the one we just introduced, but the left eigenstate is n e to the minus q. And there's the n e to the minus q. So the crucial discovery is that we've got a different quantity for the inner product. The inner product, the state n e to the minus q, is not the Hermitian conjugate of m, but it turns out it is the PT conjugate. And so the inner product is the overlap of a state with its PT conjugate rather than with its Hermitian conjugate. And as such, the inner product is positive definite. The PU oscillator.
Can I ask a question?
Yeah, let me just finish. The PU oscillator and accordingly the Pauli-Villars propagator are thus fully viable unitary theories. Yes, absolutely.
Yeah, so if you go back to your equation 28, what you have is just two decoupled oscillators. And as you say, there's no problem whatsoever with this theory. However, what I would say is that it's very interesting. If you now put in a coupling, just a simple coupling term like a coupling constant lambda times x times y, lambda xy, now as you analytically continue in lambda, you can go to this theory where you have a strictly positive energy spectrum to three other theories. One where there's a negative spectrum in the X oscillator, one where there's a negative spectrum in the Y oscillator, and one there's a negative spectrum in both the X and Y oscillator. And that is, that allows you to see all of these theories in one shot. And of course, what you can do is you can analytically continue in lambda and then set lambda equals 0, and you will see that this innocuous looking theory can still have negative eigenvalues. Okay. But you can analytically continue to them in lambda and then set lambda equals 0. So in fact, the Hamiltonian 28 represents actually 4 different theories, depending on which sheet of a fourfold Riemann surface you're on.
Mm-hmm. Yeah, I thank you very much. I would say that it represents 4 different Hilbert spaces.
Yeah, exactly. 4 different Hilbert spaces, 4 different theories, whatever however you want to phrase it. Okay,
that's correct. And this is the realization that I've given. I think is, I mean, this is one of the Hilbert spaces, and I think this is enough for my purposes. However, since you measured interactions, in a moment I'm going to add on a lambda y to the 4, and we'll see why that's important in a moment. Now, my final comment on this theory is notice that the alpha function goes like 1 over log of 1 over omega 1 minus omega 2. It becomes undefined at omega 1 equals omega 2, and the Q operator over here becomes undefined too. And this is going to be very important in a moment. But now you look at this and everything is positive. So the first question you ask is, well, where did the minus sign go? I mean, I started off with the propagator that has a relative minus sign. So where does the minus sign go? The answer is you should not identify this propagator with vacuum T55 vacuum, which is what you would think you would do. Rather, you have to identify it with vacuum e to the minus q T55 vacuum. And you have to not insert sum on nn equals I, but nn e to the minus q equals I, because that's the closure relation that we just discovered a moment ago. And that's the left eigenstate, the n e to the minus q. So now, if you evaluate this quantity with the e to the minus q, you generate this propagator, even though every state that you put in, every intermediate state, has positive norm. And it's the e to the minus q that's generating the minus sign. And Carl and I showed this in a Phys Rev D in 2008, and not the presence of the negative norm states. So what's the wisdom? The error is in thinking that D of K is vacuum T phi vacuum, because it always was in every other theory. But you can't do that without first constructing the Hilbert space. You can go from the Q number Hilbert space to the C number propagator, but you can't go the other way round. Thus, Carl and I did not actually get rid of the ghost. We showed that it wasn't there in the first place, with the reasoning that led one to think that there is a ghost being faulty. And that's, so the answer is, when you have a C number propagator, you can't just invent the Hilbert space that will produce it through a matrix element. You've got to first construct the Hilbert space. And that's the step that was missing. But now we're not.
Sorry, Philip, can I ask one more? Can I make a comment, a minor comment?
Of course you can, yes.
The e to the minus q, can I understand it as a metric in the Hilbert space? In other words, you cannot go to the flat Minkowski metric in the Hilbert space, but you need necessarily to have this e to the minus q.
No, I think you just think of it in the following way. If I just give you a skew basis, namely two vectors that are not orthogonal, I need to make a transformation to make them orthogonal. But it can't be a unitary transformation.
Right.
So but it can be a similarity transformation, and it turns out that you can write it as an exponential. But in general, if you want to transform from a skew basis to an orthogonal basis, you just need some operator, some similarity transformation.
But the metric in Hilbert space is unrelated to any.
No, this is the metric in Hilbert space.
Yeah.
Yes, I mean, absolutely.
That was my question, yeah. So,
yes, the operator that you use is the metric.
That's right, that's what I was saying.
The initial basis, yes.
So the metric is not flat, it's not the one, it's not the...
Oh, I'm sorry, yes.
That's what I was saying. Yes.
In that sense, yes, the Hilbert space metric is not the identity.
That's right, that's right. Okay. It's non-trivial.
Yes.
Thank you.
Yes.
Philip, may I make a comment?
Of course.
If you have two independent oscillators, your theory is a tensor product of two oscillators. So for each oscillator, you can define a vacuum, either annihilating annihilation operators or creation operators. So in this, you get 4 different theories which are defined by these two oscillators. This is what Carl Bender says, I think.
Yeah, as it so happens, I'm not going to do that. And the reason I'm not going to do that is because it can't be that the original theory is just 2 decoupled oscillators.
No, it depends on the vacuum. I mean, the vacuum is a tensor product of 2 vacua.
Yes.
And one vacuum somehow defines the lowest energy state, and the other maybe a highest energy state, something like that. So you define by the vacuum your theory.
Yes, but all 4 theories, the point is that all 4 of those theories are not unrelated individual theories. You can show by introducing that coupling constant that I talked about, that in fact all those theories live on different sheets of one single Riemann surface, and they're all related theories. They're not completely independent.
But the Riemann sheets are somehow a spatial representation of your annihilation creator mathematics, where you define vacua for different oscillators. And
yeah, well, we should let Philip go on, but yes, that.
I'm only resisting the suggestion that I can think of it as 2 separate Hilbert spaces, because we have to discuss what happens when we do radiative corrections. So we've looked at the 4-point function, and now with the 4-point function, we can generate a loop graph. Now I've got a propagator with a minus sign. And if I take the discontinuity across this loop, I'm going to get a minus sign. I'm not going to get the correct sign for the discontinuity. And therefore, this graph on its own violates unitarity. And that's absolutely correct. You can't look at, if you look at this graph and you just put in this propagator and you do the Landau-Kutkowski cutting rules, you'll generate discontinuities with the wrong sign. And that would be a disaster for the theory. But this cannot happen because you can't change the signature of the Hilbert space in perturbation theory. So if the theory is well behaved, then it must remain well behaved in radiative corrections. However, where on earth did the negative discontinuity go? So now we have to look at it. We'll add in an interaction, lambda y to the 4, there it is, and let's transform it with the same e to the minus q over 2 as before, and it gives me a mixture of a y and a p. And why I resisted the suggestion that I have two separate Hilbert spaces, if I can find it, is because, I have to go a little bit further back. Yes, the y is not a canonical conjugate to p. Y goes with q and p goes with x. And so when I make this e to the minus q over 2 transformation, I mix the two different oscillator sectors, and therefore I mix the vacua. But now that I've got this term, we see that it has a structure which is very different than a normal lambda y to the 4 would have. And it turns out, and this was a result I published about a year ago, is that while there's a discontinuity in the loop graph, there's also a discontinuity in the tree graph, which you never get in a Hermitian theory. However, the two of them add up so that the net discontinuity has a positive coefficient. So the theory is unitary. It's very hard to show that it's unitary because of it looks very bad for the loop, but the tree graph also gets modified, and therefore this also makes sense, because how could this theory be two independent oscillators? How could it possibly be two independent oscillators? And the answer is, well, it isn't, because the very act of diagonalizing the Hamiltonian undiagonalizes the interaction. And then you have to include both. Okay, let me just say some very quick words about antilinear symmetry. I'm sure everybody's familiar with this. You take the Schrödinger equation, you replace t by minus t, and you multiply by some general antilinear operator A, and you get this expression. And then you discover that if A to minus 1 is H, namely if H has an antilinear symmetry, the energies are either real, E equals E star, or in complex conjugate pairs. Real energies have eigenfunctions that obey A equals eta times the state with a phase eta, and the complex conjugate wave functions, A converts one into the other. In a paper I wrote in JPhys A, I showed that the necessary and sufficient condition for all eigenvalues to be real is that H has an antilinear symmetry, and that its eigenstates are also eigenstates of the antilinear operator. H being Hermitian is only sufficient for real eigenvalues. Now, while A could be any operator, these theories that date back to the work of Bender and Betcher in 1998, applied initially to p squared plus ix cubed, these theories are now called PT theories, even though the antilinear symmetry need not be PT. But nonetheless, as long as there is an antilinear symmetry, then energies are real or in complex conjugate pairs. The other way of formulating the same problem is called pseudo-hermiticity. Namely, you take a right eigenstate of the Schrödinger equation, and you introduce an operator V, and you calculate a norm, and you find that it's VH minus H dagger V. And then probability will be conserved if VH is equal to H dagger V, and if V is invertible, if VH V to minus 1 is H dagger. This is the pseudo-Hermitian condition that was first suggested by Ali in 2002. For the PU theory, we know what V is. It's e to the minus q. And the left eigenvector was R times V, and so the norm is the overlap of the left eigenvector with the right eigenvector. I went on to show the reverse. Namely, if VH is H dagger V, then the probabilities are time independent. I showed the converse, namely, if the probability is time independent, then the other result happens. And so this condition is necessary and sufficient, and therefore the most general inner product you could write down is the overlap of L with R. However, if V and H dagger are related by a similarity transformation, then they have the same energy eigenvalues. And therefore the energies of H and the energies of H dagger are the same, so the energies are either real or in complex conjugate pairs. But that's exactly what we just got a moment ago with antilinear symmetry. So pseudo-hermiticity and antilinearity are the same, and either one of them will do the job. Now, let's suppose that an eigenspectrum is real and complete. Then you can bring H to a form in which it's Hermitian by a similarity transformation. That's what real and complete means. You can always find a similarity transformation to bring it to a Hermitian form. But H prime dagger, we just take the dagger of that, is S minus 1 dagger, H dagger, S dagger. And therefore we finish up, now you just multiply through on the left and the right by S dagger, we get S dagger, S, H, S to minus 1, S to minus 1 dagger is H dagger, and therefore we can identify V as S dagger S, because there's V, H, V to minus 1. And now we look at the norm, LR, but L is RV, that's RVR, and that's R, S dagger, S, R. And therefore the norm is positive definite. And so if a theory has a completely real spectrum and the eigenvectors are complete, then the left-right norm is positive definite. Now the question is this the same as the PT norm? Now to make the PT norm agree with the left-right norm, you don't just take the PT conjugate of the ket, but you multiply it by the phase, the PT phase of the ket. And then that norm is the same as this norm. Now, the eta is the eigenvalues of the C operator that Carl introduced. And so you can think of the C operator as an independent operator, or it's the matrix of the phases, the PT phases of the right eigenstates. Now, what makes it interesting is that these phases can exist even if the C operator doesn't exist. But basically, what we come up with is that the norm is positive definite. So pseudo-hermiticity is an antilinearity. Now, for the Lie model, well, you may remember that its energies just happen to be in complex conjugate pairs. And I just showed you there's a theorem that if that's the case, the model has a PT theory. Now, the same is true for energies real, and that's the PU model, which is the Pauli-Villars theory. So both the real realization of the Pauli-Villars propagator and the complex conjugate realization of the propagator are PT theories, and in all cases, that's what makes them unitary and ghost-free. So the Lie-Wick model always was a PT theory, except it was never discussed in that language. Now, it turns out that people have taken this and developed what's called the Lie-Wick standard model, which is being used for particle physics phenomenology. And the first work on this was Grinstein, O'Connell, and Wise. Now, without the people doing this knowing it, they're actually using PT symmetry in particle phenomenology. So PT is becoming ubiquitous. Let me just comment very quickly, why did I need to continue into the complex plane? So what do we mean when we say p squared plus ix cubed, the Hamiltonian is not Hermitian, and how could the PU oscillator not be Hermitian? Now the answer is, we ordinarily think of position and momentum operators as being Hermitian. However, that only means that when acting on their own eigenstates, can one integrate by parts and throw away surface terms. It does not mean that when acting on the eigenstates of some other operator, such as the Hamiltonian, that is built out of them, that you can still integrate by parts. It's when there is a mismatch between the eigenstates of the operators in a Hamiltonian and the eigenstates of the Hamiltonian itself that one has to continue into the complex plane, into a domain where one has asymptotic convergence, and one then can integrate by parts. So looking at something is not enough. Now, let's see why it could not be enough. Let me just go back to the complex conjugate representation. Let me set omega 1 is alpha plus I2, I beta, omega 2 is alpha minus I beta, and then HPU becomes alpha squared minus beta squared minus a half alpha squared plus beta squared squared. You would look at that Hamiltonian, everything is real, and you would say that is Hermitian, but we just solved the problem and we found that the eigenvalues are in a complex conjugate pair. So looking at it is not enough. You need asymptotic information, boundary condition information. Now let's go even further. Let me set omega 1 is equal to omega 2 is equal to omega. Now the Hamiltonian becomes even simpler, and it looks absolutely Hermitian. However, the operator Q that did the diagonalization blows up when omega 1 is omega 2. It doesn't exist. And that means that this Hamiltonian with omega 1 equals omega 2 cannot be diagonalized. So the equal frequency PU oscillator is a non-diagonalizable Hamiltonian. And if the Hamiltonian can't be diagonalized, it obviously can't be Hermitian. It's called a Jordan-Bloch Hamiltonian. And why can't it be diagonalized? Because it lacks a complete set of eigenstates, something that you can't tell just by staring. You couldn't just look at that Hamiltonian and say that the eigenspectrum is not complete. The point omega 1 equals omega 2 is a transition point, and it's called an exceptional point in the PT literature, and it's the crossover point between the real and the complex conjugate pairs. And this is why there is a singularity. It's at that transition point, and it's a generic feature of antilinear symmetry. So, message: Hermiticity cannot be established by inspection. However, antilinear symmetry can be established by inspection. So antilinear symmetry goes a lot further. Now, there are many possible antilinear symmetries. Is there a preferred antilinear symmetry in nature? And the answer is yes, it's CPT. Now, the Lorentz group has a restricted sector, only Lorentz transformations, and this sector can be extended by complex Lorentz transformations to what's called the proper Lorentz group. In the proper Lorentz group, PT implements x mu goes to minus x mu, and that it's the extension to include the PT that gives you the proper group. But since coordinates are charge conjugation even, this just also happens to be a CPT transformation. Now, so let's see, how do we do this? We take a boost in the x1 direction, implements x1 prime is x1 cosh plus t sinh, t prime and so on. But we take c to be I pi. So x goes to minus x1 and t goes to minus t. Then we do it in the 2 direction, and the minus t goes back to t. And then we do it in the 3 direction, and the t goes back to minus t. So the net product of the 3 boosts sends x mu to minus x mu. Carl, in his review of projects in physics, pointed out that the linear part of a PT transformation is a complex Lorentz transformation. And I'll just make a note, and therefore, in this particular case, so is CPT. Now, when I got into the subject and I saw this remark of Carl's, I thought that that was actually the most significant aspect of PT symmetry, namely that it has a direct connection to the Lorentz group. Now, by the way, if you just were to do it for T alone, it does not work. If you do it for P alone, it does not work. You have to do it for PT because you have to reverse all 4 components of X if you want to maintain Lorentz symmetry. Now, what happens for spinors is a little more interesting. For the same operators, they implement, you just evaluate it with the Dirac matrices, and you introduce the product of the 3, now acting on the spinor space. And what you find is, if you have Majorana spinors, psi 1 goes to gamma 5 psi 1, and psi 2 goes to gamma 5 psi 2. Now, That's the transformation. And if you just look at that, you'll realize that this is the linear part of a CPT transformation. Because CPT on psi1 plus I psi 2 is I psi1 minus I psi 2. And so we recognize that this same complex transformation that we started out with as a PT transformation that gets us from the restricted Lorentz group to the proper Lorentz group doesn't do the job for spinors unless it becomes CPT. So PT alone no longer will make this transformation for spinors, even though it did do it for coordinates. And you have to introduce a second C, a C to do the job. And as far as I'm concerned, this is a first principles reason for charge conjugation. Namely, you need the charge conjugation in order to extend the restricted Lorentz group to the proper Lorentz group for spinors. And without the C, this would not work. So the linear part of the CPT transformation is naturally associated with the complex Lorentz group. But what about the antilinear part? Well, I wrote a paper that the antilinear part is fixed by probability conservation, just as we discussed before. So if you impose invariance under complex Lorentz transformations and probability conservation, you can prove the CPT theorem without needing to invoke Hermiticity. You can extend CPT to non-Hermitian systems. Only two requirements: invariance under complex Lorentz transformations and probability conservation. Now, so therefore CPT becomes the antilinear symmetry that's forced upon you by relativistic considerations. But in a non-relativistic case, when you're below the threshold for particle production, C is separately conserved and CPT defaults to PT. Thus, the non-relativistic limit of the CPT theorem that I've just described is it becomes a PT theorem. And so PT symmetry is now on a very secure theoretical footing. It has two ingredients: invariance under complex Lorentz transformations, probability conservation, and take the non-relativistic limit where you're below the threshold for particle production. And so PT symmetry in that case is preferred over any other theory. So we're coming to the end. We've seen most of the cases we've now been able to resolve, but now let's go back to the gravity problem. We had the Einstein-Hilbert action as a propagator 1 over k squared. We had the Weyl action 1 over k to the 4. We took the hybrid and we obtained this propagator. So we now know this is the Pauli-Villars propagator. This is a PT theory, and the theory is unitary, and there are no ghosts after all. The theory is fully viable. You were just in the wrong Hilbert space of using the Dirac norm if you led yourself to think that this meant that there were states of negative norm. But now let's go back to fourth order. So finally, we've solved second plus fourth. We've now shown that it's viable all along. But what about pure fourth order? If we said M1 equals M2, this decomposition into partial fractions becomes ill-defined. That limit is singular, but that's exactly what we were meeting before when we set omega 1 equals omega 2. So the pure fourth order theory itself, which is based on conformal symmetry, has a non-diagonalizable Hamiltonian. It's CPT symmetric, and therefore it's PT symmetric because G mu nu is C even, it doesn't carry an electric charge. And so the pure fourth on its own is not just renormalizable and ghost-free, it's even non-diagonalizable. And it's the last realization of PT, real eigenvalues, complex eigenvalues, or incomplete set of eigenvalues. Now, so that establishes the viability of the theory, but now comes the question: why should anyone who does not like higher derivative gravity care? And let me tell you, there are a lot of people who do not like higher derivative gravity. And I'm going to tell you why they have to care. consider the Dirac action for a massless fermion coupled to a background geometry. You just write down psi bar gamma mu d mu psi as usual, but you have to introduce what's called the Vierbeins and the so-called spin connection. Now, this was introduced in not just to couple fermions to geometry, but to make the theory locally Lorentz invariant. Namely, you make Lorentz transformations, but at different points for each phase of the e to the I omega mu nu m mu nu. So it's locally Lorentz invariant, but it just so happens that it turns out that under these transformations, it's also locally conformal invariant. You never asked it to be locally conformal invariant, but it is. You get local conformal invariance for free. Now, other than the double well potential, the entire 3x2x1 standard model is conformal invariant. It's got dimensionless coupling constants, a gauge theory. It's a conformal invariant theory at the level of the Lagrangian. What about the double well potential? Well, if you generate fermion masses dynamically, and I've discussed in this paper in 2017 how to make the Nambu-Yonah-Lacinio model, which is the paradigm for dynamical mass generation, how to make it renormalizable through anomalous dimensions, and then the entire standard model is locally conformal invariant. And what does that buy us? And this, I believe, is the last page. Yes. So I now do the path integral on the fermions of this action that I just showed you a moment ago. Yeah, the standard Dirac action. I do the path integral on the fermions, and I generate an effective action. And when you do it, 't Hooft did this in 2010, you generate none other than the conformal gravity action with a coefficient C that's log divergent. So if I start with the standard model, the one that we know and love, and I couple it to an external geometry, and I do the path integration on the psi and the psi bar, I generate the conformal gravity action. But now, the standard model goes free. It's the one we use all the time. The fermion path integral for this particular case, because it's only linear in psi bar and linear in psi, is equivalent to a one-loop Feynman diagram. But in a one-loop Feynman diagram, you're doing perturbation theory, you can't change the signature of a Hilbert space. Therefore, conformal gravity must be ghost-free, because if it were not ghost-free, the standard model would not be unitary. So, when you take 3x2x1, you couple it to an external gravitational field, radiative corrections will generate conformal gravity whether you like it or not. This is a calculation. And thus generate a gravity theory that has a PT structure. Again, whether you like it or not. Gravity thus forces PT symmetry on the standard model 3x2x1. So it's not just a nice idea, it's unavoidable. It really is there. So, summary, PT symmetry is quite ubiquitous in physics and cannot be avoided or ignored, especially in the standard model. To establish PT symmetry or CPT symmetry only requires complex Lorentz invariance and probability conservation, two perfectly standard requirements. So it is perfectly valid. And finally, if the theory of quantum gravity turns out to be conformal gravity, then one of the four fundamental forces in nature would be a PT theory. And even if that's not the case, you still have to, you can't ignore PT because it's generated by radiative corrections. Okay, thank you.
Questions?
Yeah, Philip, can I, it's Simon here. Could I ask a question?
Absolutely.
Okay, just for clarification, when you talk about the Lee-Wick model as such,
Yes.
does that I mean, I just don't know. I mean, it's obviously more complicated than the Lie model.
Yes.
There's a standard model for phenomenology. Now, presumably it has some renormalization aspects coming in, does it?
Yes, absolutely. That was the motivation. Let me
Yeah.
just
So
see
would after renormalization, does everything kind of what happens with PT and everything?
Yeah, let me state what's going on. What Lie and Wick were interested in was, could they write down a finite theory of quantum electrodynamics? Now, quantum electrodynamics, if you look at the fermion propagator, starts out log divergent. So if they were to use the Pauli-Villars propagator, then they would cancel the leading divergence. The leading divergence would in that case be logarithmic, and then they get a finite theory. And that was they realized immediately, look, these Pauli-Villars propagators, they may be a nuisance, but they really will solve renormalization problems. However, they had to deal with the issue of the ghost.
No, I'm just saying that sorry, just the Lie-Wick standard model is a further generalization, isn't it?
Okay, the Lie-Wick standard model is simply doing particle phenomenology of 3×2×1, but using these propagators with the complex conjugate pair in order to get finite matrix elements in 3×2×1.
But I mean, is there no renormalization issues? Are all graphs finite? Are you saying for the Lie standard model? Is that right?
Yes, well, I shouldn't say that all of them. I haven't studied all of them exactly, so I don't know. But the motivation dates back to Lie and Wick themselves, was to get a handle on logarithmic divergences.
But Philip,
I'm sorry, whether they've done it completely, I don't know. But I don't see why they would not get it, why it would not work. Yes.
Philip, there were several attempts to make series finite by just taking delta functions as propagators or principal values, which is like a linear combination of propagators with complex masses with negative and positive imaginary parts.
Mm-hmm.
So in a sense, if you do such a Lie-Wick standard model, you have the problem of causality, because some of the propagators, they are advanced and some are retarded.
Yes.
And the other thing is Pauli-Villars did the approach to let one complex mass somehow go to infinity to regularize the theory. Here we have this situation which is more like this delta function propagators. So how do you resolve all this problem of causality in this type of models, which always killed the models? Huh?
Okay, so let me see if I can't find it. The original propagator, the 1/k² minus m², is completely causal.
Of course.
Okay. The 1/k² minus m²² propagator is completely causal. Doesn't take support outside the light cone. Whether you have 1/k² minus m1² plus 1/k² minus m2² or 1/k² minus m1² minus 1/k² minus m2², both cases are causal. You have no causality problems with the Feynman propagator. Now you continue into the complex mass region. Now, if you just take the m² plus I gamma to be in one Riemann sheet and the m² minus I gamma to be in a different Riemann sheet, you will lose causality.
Exactly.
However, you don't do that. As you let the masses shift, you deform the contour so that both the m² plus I gamma and the m² minus I gamma lie in the same contour. Okay. And then the theory is causal. Okay. It's simply thinking that because we're used to putting m² minus I gamma on a second Riemann sheet, that therefore we should do it here as well. But the answer is no, you don't do that.
So
in other words, what you're doing is you're creating a violation of causality by using a wrong contour. In other words, if you just keep the contour that you had always used for real masses, that one will give you a problem. So what I'm saying is that if you let, as the masses become complex, if you let one of the masses cross over into a different contour, then you will lose causality.
Okay. But choosing the contours is like choosing the boundary conditions.
Absolutely. Yes, you can choose any contour you want.
Other question.
That's your choice.
Other question. By your construction, you somehow extended your action of gravity from the Einstein action to a more sophisticated action.
Yes.
Does this have implication for electrodynamics? Maybe is electrodynamics in its sense not complete? You need to extend somehow electrodynamics also?
Absolutely not. It's the other way around. You could ask a question which nobody asks, and that is, why do we take electrodynamics, weak interactions, QCD, SU3 cross SU2 cross U1, why do we use second derivative theories?
Is
And
they are non-abelian or what?
Abelian or non-abelian. Why do we write down kinetic energies that are second order? We take dimensionless coupling constants. We have a renormalizable theory. But why do we do that? And the answer, well, you can say, well, that's because it works. But what is there a principle that would tell you why you should be using dimensionless coupling constants? And the answer is yes, it's conformal symmetry. So if you impose conformal invariance as a starting point, and it's a reasonable starting point because it's a symmetry of the light cone, and all particles move on the light cone before they get masses, if you do that, then you will be forced to second order electrodynamics and not to a fourth order variant of it.
But
however, one second. But when you do it for gravity, you are forced to abandon the Einstein-Hilbert action and you are forced to go to the fourth order conformal action. And I got into this subject in 1989 because that same procedure makes the cosmological constant zero. And that's why I got interested in it. Namely, conformal symmetry controls the cosmological constant. That's why I thought about it. But you see, what it does is this same symmetry makes every theory renormalizable, but the surprising thing is it makes gravity fourth order, even while it really leaves electrodynamics second order. I'm sorry.
But the most theories we consider in a simple way, they have the triviality problem. If I put up the cutoff, my series get trivial. So can it mean that you can avoid triviality by making a higher order derivative series?
Yes, okay. You have to pay a price, which is a reasonable price. And that is, beyond the triviality issue, conformal symmetry is violated in perturbation theory because the cutoff is not conformal invariant. How do you get around that? The answer is, you have to be non-perturbative, you have to be at a fixed point, and at the fixed point you have scaling with anomalous dimensions. That's, as far as I can see, that's the only way to make these theories viable. The other, I could have said to you, if I go back to electrodynamics, and I just do radiative corrections, I find a Landau ghost, namely a state that's in the deep Euclidean mass with a negative residue. If I do renormalization group and I improve and I sum more and more graphs, the norm of that state does not change because it can't change in perturbation theory. However, one thing is left. Could the residue at the pole, instead of being negative, could it be zero? And the answer is yes, if you have a fixed point. So the fixed point will solve the Landau ghost problem, and at the same time will allow radiative conformal corrections to be valid. And so most of my career, I've started out with the assumption that the only sensible field theories are ones which have a fixed point. And of course, I've run into enormous problems because the standard treatment of QCD and asymptotic freedom is to say there's no non-trivial fixed point. So if I'm not just in left field on conformal gravity, and I'm not just in left field on non-Hermitian physics, I'm also in left field on fixed points.
Very good, thank you.
You're welcome.
Can I ask a question?
Absolutely.
You mentioned about, I mean, it's very interesting, this CPT, I am very happy because I've always, in fact, I've been discussing with Carls in the past, I've always been thinking that the PT is actually the CPT in the more general theory. However, I have two questions. My first question is locality. In the standard Hermitian CPT theorem, locality is one of the requirements. Here, did you avoid locality or you implicitly assumed it? In other words, could you have non-local?
No. Locality is not needed for CPT. It's needed for spin and statistics.
Well, in the standard CPT, locality is one of the assumptions.
Actually, the proof that I gave you.
That's my question.
No. Let me answer your question. The proof that I gave you, I actually started out with Weinberg's textbook on quantum field theory, and he proves the following theorem. It says every even integer spin state or representation of the Lorentz group can be made to be CPT even, and every odd integer spin state can be made to be CPT odd. That's his theorem. But the Hamiltonian has to, the action has to be even spin. And therefore it's a product of two CPT, if you had two CPT odds, you multiply them together and you get a CPT even. So with that theorem, every term in the Lagrangian is CPT even. However, you can multiply them by coefficients. And those coefficients could be complex. And so what Weinberg said was, well, if I assume that the theory is Hermitian, those coefficients are real, and then I have CPT invariance. And that makes none of the high-powered stuff that you get in Streeter and Whiteman. It really is very direct. And I realized that everything he said is true, but I can make the coefficients real by probability conservation. And then I don't need hermiticity. So
is not hermiticity, which I said, is locality.
No, I'm saying is that Weinberg's proof of the CPT theorem assumed hermiticity and
that I agree.
Did not assume locality.
Okay. Now my second question. You are familiar with the theorem by Greenberg, who was saying that Lorentz symmetry is fundamental and implies CPT, all right?
It would be a nice theorem, but I'm not familiar with it. You'll have to tell me.
There is a paper in the physical letter. I can send you the reference, but that's not my question. My question is, in that theorem, when he assumed that Lorentz symmetry implies CPT, is implicitly he assumed that the scattering, the S matrix, is well defined.
Yes.
In your theory, this is your S matrix is well defined. Am I right? Or
no. I have a theory of massless particles.
No, the S matrix. The scattering.
I'm working with massless particles. The whole discussion of S matrix theory changes for massless particles.
Yes, but
I can do photon-photon scattering or graviton-graviton scattering.
Yeah, but that's not my question. My question is, if you have, as you know, in quantum gravity theories, you have because you mentioned that conformal gravity could be embedded in quantum gravity. You have the coherence in which the S matrix is not well defined. There, the CPT operator is not well defined. Not well defined. It depends. So my question is, do you really? So is the PT saves you? In other words, if you have a PT, can you say something about the S matrix or not?
Yeah, I mean, if you want to construct the S, okay, maybe this is the answer to your question. If you want to construct the S matrix in a non-Hermitian theory,
yes,
it is not ket in, bra out. It is ket in, bra out times e to the minus q.
That's right.
In other words, it's right in, left out.
Right.
And that's the one that you have to use in the non-Hermitian case.
Okay.
And I don't know of people that do that.
Right.
I mean, usually, you see, what PT symmetry is basically telling you is everything that you usually do has a hidden assumption.
Mm-hmm.
And you have to unravel it. So the definition of the S matrix changes. In fact, when I told you a moment ago how I was able to finish up with a positive signature for the discontinuity in a loop graph, it was because I had to change the definition of the S matrix. I had to use left in, right out. And that's the correct one. And I'm not aware that there are any difficulties with that. But if you're going to use, let me say it this way. If you're going to use right in, right out, maybe just Hermitian conjugate out, then you're using the Hermitian definition.
Oh yeah, that's that I agree.
And so everything that we already know about CPT must hold.
Yeah.
You may not have realized it, but it's built in, it's automatic. It's only when you realize that you have to change the definition of the S matrix that that you can see that there's a richer set of options. And that's why I focused on the CPT theorem and asked, what is the minimum set of assumptions that I need in order to establish it? And the really nice one, and this was I got from Carl's Reports on Progress in Physics paper, was complex Lorentz invariance. And now Carl and I are sort of a little bit different because we don't regard complexes in any way unusual.
Thank you.
Philip, can I just ask one thing here? What about, do you have in all the stuff that you're doing concept of broken PT symmetry?
Broken PT symmetry is a term that Carl introduced to differentiate between the realization where all the energies are real and the realization where the energies are in complex conjugate pairs. So in that particular case, PT is still a symmetry of the Hamiltonian, and the broken term just means complex conjugate pairs. Now, you ask a separate question, which is, could PT itself be spontaneously broken?
Yeah.
And that's just the same as any other symmetry. All symmetries can in principle be spontaneously broken. Spontaneously breaking an antilinear symmetry is not simply a generalization of spontaneously breaking a linear symmetry. But so if you're asking,
I'm not sure what you mean actually by making that distinction. What's the difference between broken and spontaneously broken?
Oh, because you're asking that there exists a field with a PT symmetry that takes a non-trivial vacuum expectation value. Let me put it there. Carl, I think from the beginning when you introduced the term broken for the complex conjugate phase, I think you had that in mind. But I don't think that it has to be anything to do with spontaneous breakdown. Now, I don't see any reason, any immediate reason why spontaneous breakdown would automatically get you into complex conjugate energy eigenvalues. I mean, maybe it does, but I don't know that that's been discussed anyway.
I don't know if that language actually applies here. I really don't.
Well, that's what I was answering, is that the use of the term broken in the way you're using it and the term spontaneous broken are two different concepts. But I'm not sure. Sarban, was that what you were asking initially?
Well, I was just thinking that in the theories that you have, do you I mean, with the field theory type of stuff, do you actually have any concept of a broken PT? I mean, that's something that you don't necessarily work out the eigenvalues or anything like that. That was my. I mean, would you have a situation when you have like in the quantum mechanics situation when things are broken and you have not a that's the difference between a Hermitian theory and a PT symmetric theory, isn't it?
Okay. I'm going to be a little bit awkward. In this paper I wrote on the CPT theorem, I actually had a proof that CPT could not be spontaneously broken. But I don't immediately remember how I did it. But that allows for the possibility that C and P and T could all separately be broken without CPT being broken. I think it seems to me, I would expect that PT symmetry could be spontaneously broken. I mean that you can do it consistently, not necessarily that it's realized in the real world. Especially since we see, let me back up a second. We know that parity is violated in weak interactions. We know that PT is violated in weak interactions. Now, people like me work in chiral theories, and in chiral theories, the violation of parity is spontaneous, not just, you just don't write down an SU2 left as the given Lagrangian, you take SU2 left cross SU2 right. So if parity is spontaneously broken, and in the real world we see violations of PT, I would anticipate that PT would be spontaneously broken too. But the models that I've been describing, even with the complex conjugate pairs, are not in that category. But I think it's an option that needs to be explored.
Can I just say, this question of the breaking of PT symmetry is actually really, really complicated. It's complicated because, I mean, the reason you can have a breaking of PT symmetry is simply this. Even if the equations of motion and the Lagrangian and the Hamiltonian and so on, the governing equations of the theory, even if they have PT symmetry, there's no reason why the solutions to those equations have to have that symmetry, and everybody knows that. Yeah, okay, absolutely. So you can have a situation where the Hamiltonian is PT symmetric, but some of the states of the Hamiltonian have complex eigenvalues, and there's no reason why that cannot happen, okay? The question is to understand what the physics is when you have a broken PT symmetry, okay? And the physics can be very, very complicated, and even defining what you mean by an inner product is not at all clear. And you have, you know, there's people that have used the term self-orthogonality and so on. These are very complex issues. And in fact, Philip, a long time ago, we once had a brief discussion saying that the world has to be PT symmetric because it's clear that the Hamiltonian is not Hermitian because there are states of complex energy. Yeah. Okay, but in fact, once you have a state of complex energy, defining an inner product is non-trivial because you can't analytically continue from an unbroken state to a broken state. Yes. Okay, so defining a probability, defining the C operator and so on, all that is very complicated. We could have a long discussion about that, but not here.
Okay, Carl, there's a simple example where a theory breaks symmetry.
Frida, let me just comment on Carl. When we had talked about PT always being an exact symmetry of nature, I was hoping that it would be, and I realized that not quite, it has to be CPT. Yeah. And so, but the issue you raise about the complex conjugate pair is you can have time-independent transition amplitudes between the positive imaginary part and the negative imaginary part. And those are the only non-vanishing matrix elements that, in other words, you don't overlap a state with its own conjugate because its own conjugate, you don't change the sign of gamma t. You overlap it with the partner. And all of the discussion, all of the discussion that I've seen in the literature is, in my opinion, is doing decays wrong, to be completely honest with you.
Yeah, in fact, it is very clear to me that when you try to define what is meant by an inner product in the broken region, when you have complex energies, that inner product has to involve ingredients from both states, the state
Exactly.
and its complex conjugate.
Yes, in fact, it's here. It's basically, it's what Lee Wick are doing without saying so.
Yeah.
It's the interplay which generates the correct phase. Absolutely. I'm sorry. So Frida, yes.
Yeah, well, there is a very simple example where the action or the theory contains a certain symmetry, but the symmetry in a sense could be broken, and this would be somehow an anomaly through the path integral, where you have, for instance, a determinant which can introduce things which are very nasty. Yeah. So I think the question is if the consistency of such a quantum theory would introduce such a somehow spontaneous breakdown of PT symmetry, even if the theory appears to be in general PT symmetric.
Well, anomalous violation of the symmetry is not spontaneous breakdown. It's happening in the original Hilbert space.
Yes, but as you see, the Pauli-Villars method generates ghosts, yeah? And so they come not from the theory, but from the determinant of your path integral. So
you're thinking about Fadeev-Popov?
Anomaly usually comes from the phase space of the path integral and not of the from the action itself or
yes.
anything.
Yes. Mm-hmm. Well, I don't know of any discussion of generating anomalous violations of anti-linear symmetries in path integrals, which is I mean, I'm not saying that it can't happen. I just say I'm not aware of any. And the reason is when you do QCD, you're working with the PT symmetric theory. I mean, you're not thinking about spontaneously breaking or even anomalously breaking a discrete symmetry. But I do think that somehow in the real world, PT is going to be spontaneously broken, rather than anomalously broken, or simply just not in a symmetry to begin with. But I haven't worked on that. That's for the future.
Philip, my opinion about this is to formulate consistently a quantum theory, you need a causal and the anti-causal part. The anti-causal part, it is somehow a parallel universe which you never reach, but you need it for consistency. So in itself, you have PC symmetry in the full quantum theory, but you are living just in the causal world, which is somehow the part where all the boundary conditions go in a causal way. So, and when you then live in this causal world, you can generate spontaneously causal complex masses, for instance, for quarks or anything. So in a sense, to have a consistent quantum field theory, you need both the causal and the anti-causal part. In all theories where there appear somehow complex energies, you have to double the degrees of freedom to get somehow consistency in your theory. But you use only half of the degrees of freedom.
I'm not sure what you're saying. I'm not disputing it. If I want to, I mean, in the end, what I have to do is calculate a contour integral, and I can close that contour any way I want.
Yes,
now,
but
usually what we do is we say, well, we want to suppress the circle at infinity, and therefore we'll close it above in certain cases and below in other cases. But that's not necessary. You can close it below, you can include the circle at infinity, and you can still evaluate the function, and you'll get the right answer.
Right, but there's a certain
you never need. In other words, you can trade what you're calling the you can trade the advanced sector for a circle at infinity in the retarded sector.
look, there's a certain ordering. Either you can write down your Hamiltonian and make your theory and later choose somehow your boundary conditions by choosing your vacuum and your contours, or you can work from the onset with fields which are complex. We had these discussions 1 week ago with Nikolaos, where he showed two equations, which on the left side was imaginary, on the right side they were real. And I said you should treat the fields from the beginning as complex functions. Then you do not miss this point, and then you do not need to choose any more integration contours, because you somehow have, by choosing complex fields, already chosen somehow your boundary conditions more or less, if you define your masses with a certain imaginary part. But if you make your fields complex, somehow you have not only one real degree of freedom, but two. You double your numbers of degrees of freedom. And then you work only with the complex fields and not with the complex conjugate complex fields. So somehow you choose only half of the mathematics, but you have a theory which in a sense is PT symmetric because they contain both. This makes them somehow mathematically valid. Yeah.
I mean, the issue that you're asking is not, you don't define a field by whether it's real or complex, even though I do it myself all the time. You really need to define a field by how it behaves under CPT.
Yes, but the CPT behavior is somehow reflecting what you would make if you from the onset start with a complex function. You choose from, go from a complex function to the complex conjugate. In mathematics, you would discuss about holomorphic and anti-holomorphic functions and fields. You have, this is this kind of ordering. In most textbooks, you start from somehow real fields and later you insert boundary conditions. But if you from the beginning start with complex functions, you certain fix your problem already from the onset, and you do not need to talk anymore about the C operator.
Okay, let me go back to, I hear what you're saying. Let me go back to something very simple. Look at the commutator of X with P. It's equal to I, or IH bar. Take the complex conjugate of that equation. You get X conjugate, P conjugate is equal to minus I. Therefore, at least one of X and P must be complex. And the usual way we do it is we write X is A plus A dagger, which means that it's a real matrix. And P is I A dagger minus A, which means it's a complex matrix. So from the very beginning, even in elementary quantum mechanics, the commutator of X with P is IH bar, is represented by P being an infinite dimensional matrix, all of whose non-zero elements are pure imaginary.
But if you take the Hermitian conjugate of your commutator, the sign of I doesn't change because the commutator inverts.
I'm not taking the Hermitian conjugate. I took the complex conjugate.
Or the complex conjugate,
When
yes.
I take the complex conjugate, I discover that if I want X to be a real matrix, a real infinite dimensional matrix, then P has to be a pure imaginary infinite.
Okay, that's
matrix.
right.
So even though P is still Hermitian, it doesn't matter. You write it as I A dagger minus A, and its Hermitian conjugate is I A dagger minus A. It's absolutely Hermitian, but that does not mean that its infinite dimensional matrix representation is real.
Okay.
It could be anti-symmetric and pure imaginary, just like sigma 2.
Right.
So when you give me a field, you can't tell me that it's real or imaginary. What you can tell me is how many independent components it's got. So if you wanted to write phi as phi 1 plus I phi 2, you're saying that phi has two independent components which transform as scalars under the Lorentz group.
Right.
And the only question is, can you relate phi 1 and phi 2 by a CPT transformation?
Right.
But the notion of the number of degrees of freedom of a field is really how many different Lorentz representations are combined into that field.
It's
not a question of is it real or imaginary, because real or imaginary has no absolute meaning. Because I just said with X and P as IH bar, I could do the reverse. I could make X pure imaginary and P purely real. That's just another realization of the same commutation relation.
Philip, I formally quantized a Klein-Gordon field with complex mass, and I needed to take the complex conjugate or the Hermitian conjugate, and then I was back to a theory which was made up by Nakanishi, and it turned out to be PT symmetric because I had to double my creation and annihilation operators.
Okay. I'll give you an even earlier example of that same phenomenon. Take the Klein-Gordon equation with the wrong sign for the mass.
Right.
Okay? Minus m squared instead of plus m squared. You can solve the wave equation, and the energies are the square root of k squared minus m squared. So for large enough, for small enough k, some of the energies become imaginary.
Right.
Even though the Hamiltonian is just p squared plus p squared minus m squared. There's no sign of any non-hermiticity. But what you do get is, for every complex conjugate, you get the complex, for every imaginary solution, you get another one, which is the complex conjugate. And therefore, in that realm, you're in a PT theory.
Exactly.
You don't need to go to complex masses. You can just go to negative mass squared. Just the tachyon. If you just quantize the tachyon as is.
Exactly.
Frida and Philip, it becomes now a private conversation, and most people have left already.
That's fine.
Maybe we should stop it here, and you could get in touch and continue the conversation. Yeah, is that
certainly?
Well, I'm happy to to do whatever you want.
Most people have left now, and it's essentially you two talking now. Yeah.
Okay.
So maybe we allow people to leave as well. The remaining one is not many people left now. Yeah.
Does anybody have an urgent question? Oh, someone's phoning me.
Okay, I leave. Thanks very much, Philip.
All right, there we go. All right,
thanks everybody.
Hi, thank you.
So thank you.
Thank you very, very much, Philip, for the nice talk.
Yeah, thank you all for listening.
Thank you, Philip.
Thank you.
Bye bye. Bye bye.
Bye bye.